Okay, thank you very much. So I think it's very appropriate that this year we talk about this history, this part of history of our field, because in fact it so happens that the year 2024 marks the 50th anniversary of a phase transition in our perception of fundamental physics. By the late 50s, the high-energy physics landscape was fragmented in many disconnected domains, having no common trends and often ignoring each other. For strong interaction, we had the main approach, which was based on the analyticity properties of the S-matrix elements, which gave very important and interesting results. But it was not a general theory. This was the general approach, but then there were simple models like, say, peripheral model or multi-peripheral model, or iconal approximations or longitudinal phase space approximations, whatever you want. None with any solid theoretical basis, each one applied only to a particular corner of the phase space. For weak interactions, we had the Fermi theory, which proved to be a very good phenomenological model, but it had no logical justification and no obvious connection with anything else. And this separation was not only for the subjects, but also for the community. People who were studying strong interactions did not know anything about weak interactions and vice versa. So the community was fragmented in many subsets of people. Wait a minute, let me close that. During this period, the only real progress we had in our understanding of nature's fundamental laws came only from the application of symmetry principles and not from dynamical calculations. We didn't have really any dynamical calculations that could tell us something about nature. Quantum field theory was noticeable mainly by its absence. Totally marginal subject confined to very few precision calculations in quantum electrodynamics. Many physicists had only vague and often erroneous ideas about it, and to a certain extent this misunderstanding has survived even today. Even today you find people who have not understood really quantum field theory. The phase transition from many models to one theory occurred half a century ago. It was, I would put it, in the 1974 London conference, although it was more like a roughening transition. It took some time, maybe 1 or 2 years around that. And the order parameter was the percentage of theorists which changed their views. Before 74, I would say that the great majority of theorists did not consider the standard model. The standard model was already complete by that time, but the great majority of theorists did not consider it as an interesting or fundamental or new or whatever work. And after that, the great majority changed their views. For most of us, this transition was a revelation. For some others, it was a painful experience. It is this story that I will attempt to narrate in this talk, although I do not consider myself to be an unbiased observer. So let me start with the background of what I call the origins of particle physics. If I had to assign a year to the birth of experimental particle physics, I would choose 1950, the discovery of the neutral pion. It is the first elementary, quote-unquote, particle discovered with an accelerator, and the first whose existence was predicted based on an argument on internal symmetry, in fact, isospin. The existence of pi0 was predicted by Nicholas Kemmer in 1938 when he wanted to write an SU2 invariant interaction between nucleons and pions. And then he realized that you needed a pi zero. You could not do it only with charged pions. Incidentally, I think that the community has been extremely unfair to Nicholas Kemper. His equations are in all textbooks, the pion-nucleon isospin invariant Lagrangian, but his name is rarely mentioned. Since that time, accelerators became the main engines of discovery in particle physics. The field expanded very rapidly. This was one thing, but also the nature of experimental work changed. Before, a team of an experimental team would design an experiment, build the apparatus, perform the experiment, analyze the results in their labs. With the accelerators, these functions have been rather disassociated. You could have, because you have large collaborations, some of them would be more important in building that part of the detector, and some others were more important in doing analysis and things like that. Furthermore, the net result was an exponential growth in the number of elementary particles. Although we know that all entries in the particle data group, in the tables of the particle data group, are not elementary, but they form what we call elementary particles in the sense that they are objects of our studies. Now, if I look on the contrary of the theoretical physics, particle physics, this has a very precise date of birth. It's June 2, 1947, the Shelter Island Conference. The most important contributions which were presented in that conference were not theoretical breakthroughs, but two experimental results: the non-zero values of the lamp shift and of the electron anomaly's magnetic moment. They showed beyond any possible doubt that the predictions based on the Dirac equation for the electron are only approximately correct. Shelter Island is a landmark of theoretical physics. Oppenheimer has said, who was the main figure in this conference, that it was the most successful scientific meeting he had ever attended. I also quote Steven Weinberg, who was saying that the great thing accomplished in this by these discoveries, I mean the lamp shift and the lamp shift, was not so much that it forced us to change our physical theories, as that it forced us to take them seriously. Indeed, the formalism of quantum field theory existed already for both bosons and fermions. But the enormous prestige of the Dirac theory on the one hand, and the absence of a clear physical motivation on the other, discouraged theorists to face seriously the problem of the divergences of perturbation theory. The fact that the theoretical ideas existed already in a subconscious form is witnessed by the fact that it took practically no time to develop them. In the following months, Feynman, Schwinger, Tomonaga independently in Japan, and Dyson set up the program for the renormalized perturbation expansion of quantum electrodynamics. The Shelter Island Conference was meant to be the first in a series on the same subject. The subject was Foundations of Quantum Mechanics. Indeed, a follow-up conference was in Pocono, Pennsylvania in 1948, and the third one in Old Stone, New York in 1949. After that, after 1949, the program of the Foundations of Quantum Mechanics was declared complete. So there was no fourth conference. We had finished. Well, today we know that this was a rather optimistic view, but at the time it seemed to be justified. The results obtained by applying to quantum electrodynamics the newly established principles of renormalized perturbation theory were in spectacular agreement with experiment. So everybody was confident that things would be resolved pretty soon. From now I go to another, from euphoria to disillusionment. The natural next step, of course, was to apply this approach to the other interactions, the strong and the weak. The results were disappointing. The strong interactions were too strong, so the perturbation expansion made no sense. The effective Copley constant was of order 10, so the power series expansion in powers of 10 is not very useful. Remains the weak interactions, as obviously they are weak, but they turned out to be too singular. The renormalization program is a complicated set of rules, if you want, and they don't apply to all theories, only to a very small number of quantum field theories. Well, the weak interactions is not among them. The Fermi theory is not one of them. This double failure soon tarnished the glory of quantum field theory. The disappointment was such that the subject was not even taught in many universities. When I entered graduate school in 1962. There was no course on quantum field theory, and I chose the option particle physics. There was no course on quantum field theory. We entered what I call the dark ages. Many models, no theory. Those of us who were students during these lean years had lost hope to live a moment of excitement. We were thinking, oh, well, physics is dull. It's not interesting. Well, you have small calculations right and left, but nothing really. And in fact, I remember several people left the subject because of that. They were disappointed. Even the founding fathers appear to be losing faith. Freeman Dyson wanted immediately after he established this thing, wanted to prove that the series was convergent. Well, he knew that it could not be completely convergent, but he thought that somehow if he could, because otherwise you would find, say, bound states like the electron and the proton later. But somehow he thought that if you go to high energies, the series would be convergent. And as you know, he did not prove that, but he even proved that it was not true. So then he wrote, so my program for making quantum field theory consistent by purely mathematical manipulations without any new physics came to an ignominious end. The hard-earned lesson is that new physics is unavoidable. Feynman in 61, he was talking in a conference given this was the Solvay conference in 61, and he was giving a summary talk, and then he on field theory, and he mentioned the fact that for him a good theory would be the one that would allow to compute mass ratios or mass differences or something like that. And since quantum field theory did not allow to do that, he said that the theory must fail, and I do not subscribe to the philosophy of renormalization. Schwinger, as you know, by the late 60s, lost interest in quantum field theory and attempted to develop a new approach called source theory, today forgotten. Then started what I call the secret road to the new theory. Now, this road was long, circuitous, and not very well defined. In many a time, it gave the impression of leading to a dead end. In fact, it was a long series of isolated and mostly confidential contributions. Essentially, all the milestones went unnoticed when they were first proposed, and we shall have plenty of opportunities to signal that, whether it's Gates theories, spontaneous symmetry break-in, Brownian-Higgs mechanism, all these things were invented for totally different purposes, not for the ones that finally were used, and nobody paid any attention to them. Many important ideas had to be rediscovered again and again because people did not, there was what I call an over-compartmentalization compartmentalization of theoretical physics. People knew only their own little field, and they did not read papers a little bit outside this field. Therefore, they had to, when they needed something, they had to rediscover it. The protagonists were not aware of each other's, and sometimes, as we shall see, even of their own work. Shall see some examples of people who had forgotten what they had done themselves several years earlier. Research resembled a random Monte Carlo algorithm. Many random directions in the phase space of ideas were explored, and it's only now that we can see a coherent picture. Most of the ideas which eventually built the standard model were proposed for totally unrelated purposes. So this makes the task of the narrator, of the historian, very complicated because it touches very many disconnected pieces. I will try to do a partial work the best I can. Well, which were the main theoretical ideas that constitute the framework of the standard model? Well, theory of renormalization, the renormalization group, gauge theories, spontaneous symmetry breaking, the Brown-Engler-Higgs mechanism. All these things would make, if I tried to tell the story of any of those things, would make for a passionate story, which would take more than an hour and a half. However, most of when you look at the early stages, they were totally unrelated to the standard model. So here I will not develop any of them in detail. I will present instead a personal selection of various contributions coming from all these chapters. They are not necessarily the most important contributions. They are mostly those in which I was personally involved. So, Young-Mills theories. Well, the main step is the 54 paper by Young and Mills. It is an SU2 theory, which was aimed to describe the nuclear forces, SU2 for isospin. It has never been used for that purpose. So this, however, if you really want to see the story of non-abelian gauge theories, it goes much, much earlier, much before the war. In the 30s was a paper by Oscar Klein, but I won't go into that because it will take too long. So in particle physics, we called immediately these theories Young-Mills theories, right? So, and it was important because Young and Mills were the first who understood that, you see, all the previous attempts tried to tie local symmetries with diffeomorphisms. So they consider them as parts of general relativity. Young and Mills, to my knowledge, were the first to realize that if you talk about the gauge theory of an internal symmetry, it takes place in a fixed background space, which can be chosen to be flat, in which case general relativity plays no role. So since 54, non-abelian gauge theories, at least in our community, are called Young-Mills theories. Now, as I said, they were meant to be applied to isospin, but in fact, they have never been applied to that. The first application I could find was Swinger in 57. He wrote a model with weak interaction, in fact, it was weak and electromagnetic interactions with vector bosons. It's an SU2 model, electroweak model, and the neutral boson was the photon. A year later, Brudman wrote an SU2 weak interaction model, in which all currents were V-A, both neutral and charged. It was the first model with a weak neutral current. In 61, Glashow and Gell-Mann wrote a generalization of Young-Mills. Young-Mills was for SU2, and then Utiyama wrote a generalization to other groups. Glashow and Gelman in 61 considered an algebra which was direct product of simple algebras. And many results which became standard, like one coupling constant for each simple factor of the algebra, also possibility of charge quantization and problem, all these things were first mentioned in this paper. For some reason, this paper is confidential. Most people don't know it. I suspect that the reason is the authors themselves, mostly Gelman, who practically never referred to it again. So the paper which I consider that has, from all this list, has passed the test of time is the paper by Glashow 61, which everybody knows because it's the one that gave him the Nobel Prize. It's an SU2 cross U1 model for the electromagnetic and weak interactions. The photon is a linear combination of the fields associated to U1 and the third generator of SU2. And he has the angle called theta, which today we call theta W. The joke that Shelley Glashow makes is that W stands for Glashow. It's the last letter of his name. In all these models, the masses of the gauge bosons were introduced by hand. Gelman and Glashow had noticed that the resulting breaking of gauge invariance and talk about partially gauge invariant theories. So now I start a second story, which is spontaneous symmetry breaking in the presence of gauge interactions. I will not talk about the part of spontaneous symmetry breaking of global symmetries, Nambu, Goldstone, and Nambu, John Alcinio, right? So I go directly to the Broughton-Glare-Higgs mechanism for reasons of time. In fact, this is another complicated story because there are two parallel stories. They developed independently and mostly ignored each other. The first is the Meissner effect in the theory of superconductivity. And the main actors there is the basic paper of Landau and Ginzburg of 1950, in which they introduce an order parameter. They study this phenomenon as a phase transition from the normal conductor phase to the superconductor phase. And the order parameter is they introduced a function which they call psi, which is the order parameter. When this is non-zero, then there is a spontaneous symmetry breaking and the photon becomes massive. Then in 57, mostly this paper, say, if you look at the papers of Anderson and Nambu, they do not refer to the Landau-Ginzburg paper. Bardeen, Cooper, and Schaefer wrote their BCS theory in 57, and immediately in 58, Philip Anderson understood really the phenomenon in terms of phase transition and showed that the Cooper pairs play the role of what would be called today the Higgs field, if you want. So it's a series of very nice papers. And he proves that all the phenomena are there as we know them together today. There is a mass gap in the energy spectrum, so there are no massless particles. And also there are longitudinally transverse waves, plasma waves, which proves really that the photon, or whatever you call it, has become massive. In 1960, Nambu wrote more or less the same thing. He refers to Anderson. To our language, quantum field theory, Nambu is easier to read than Anderson because he uses more our language of quantum field theory. Now, what about particles? The other story is in particle physics. Well, the first person, as far as I know, who really questioned the connection between gauge invariance and zero mass was Finger in a series of papers in 62. In fact, Swinger, I guess that Swinger understood that because he looked at the Swinger model, two-dimensional quantum electrodynamics with massless electrons. It's a perfectly well-defined theory. It has, you can apply perturbation theory. It has what you would call electrons, and you has what you would call photons, and there is no mass gap. However, the model is solvable, and when you solve it exactly, you find there is a mass gap. So this made Swinger think and understand that the connection between gauge invariance and massless photons or gauge bosons is only true in perturbation theory. In fact, he had understood, the papers date from 62, but he had understood even before, because in a conference in 61 in Aix-en-Provence in France, Feynman, who gave the summary talk, referred to Swinger and said precisely that Swinger has explained to me, he said, that this connection between photon and between gauge invariance and massless photon is only true in perturbation theory. There were then a series of papers. Maurice Levy wrote something, a non-local QED with massive photon. There was a series of papers by Benjamin Lee and collaborators who tried to find models. The idea at that time was, can we find for relativistic particle theories the same phenomenon that you see that Anderson had seen in superconductivity, namely spontaneous symmetry breaking that results to a massive photon or gauge boson. And then came a paper by Gilbert, which is very interesting because, well, Gilbert really, although of course his interpretation was wrong, the paper is very interesting because it is the first model-independent proof of Goldstone's theorem. Until that, the theory of Goldstone's theorem was in specific field theory examples, scalar fields that would take m squared negative and things like that. Gilbert gives interesting proof which is does not require any particular model, and in fact he tries to make it axiomatic in some sense. He said, let's assume that I have a theory which is relativistic invariant, local, and has a positive definite metric in the Hilbert space. Well, he does not, this last one, he does not say it explicitly, but it's understood, the positivity is meant there. And then he proves that if you have all these ingredients, then the spontaneous symmetry breaking implies a massless field, which means that you could not have relativistic generalization of the Anderson phenomenon. But then, completely independently, in the same year, 64, Braut and Egler wrote their paper, which they have the mechanism as we know it today. Both for abelian, non-abelian. It's a very complete paper. They have has practically everything we have today. The purpose was for strong interactions. They wanted to break spontaneously SU3, Gelman SU3, and give masses to, say, Rocky star and things like that. Okay, so what was wrong with Gilbert's proof? Well, the Gilbert's proof, finally, the person who understood what was wrong was Higgs. In his first paper, Higgs answered Gilbert's objection, and he answered by counterexample. He presents a full study of an abelian model and considers the gauge, the Coulomb gauge, which is not relative, does not have relativistic invariance, and proves that in this case, you have really the phenomenon applies and the photon becomes massive. And then he said, physical results like the masses of particles cannot depend on the gauge. So it should be true even in another gauge. Then he wrote a second paper in which considers everything again like the Gengler-Brown. And then finally, this final paper was Guralnik, Hagen, and Kibble, which in fact it's a rather complete discussion of the phenomenon, and they really point out what was wrong in Gilbert's analysis. You see, you cannot, if you have a gauge theory, you cannot assume simultaneously relativistic invariance and positive definite, say, Hilbert space with only positive definite metric states. Because if you choose a gauge like a covariant gauge, whichever you want, then you have to quantize in a Gupta-Bloiler metric in which there are negative norm states. And technically, Guralnik, Hagen, and Kibble point out that in Gilbert's proof, you consider the charges, which are the integrals over free space of the zero component of the current, and these integrals, if you have spontaneous symmetry breaking, you have first to define them in a finite volume and then study carefully the infinite volume limit. So with this paper, I think that the phenomenon was clear. In all these works, the emphasis was on possible applications to strong interactions, flavor symmetry, no reference to weak interactions. In fact, I was at CERN as a fellow in '65, and Robert Brout came and gave a seminar on this paper, and he talked about the breaking of say, Gelman and Neyman SQ3. And well, I have to confess that I did not understand much of what he said, but I discovered also that I was in good company. Most of the people in theory division had not understood the point. Well, today it sounds very simple, but apparently it was not. Took some time for people to understand what was going on. And also, you can see it also if you look at, I will mention again for other things, look at the references, all these papers, if you look citations. In the first years, they have practically no citations. And only after we understood the importance of this work, then the number of citations goes up. So the synthesis of all that was a model of leptons by Weinberg in '67. See also Salam, a year later, Salam gave the same thing. Apparently, he had it also in Imperial. He had given seminars on the same subject. So, in these papers, in a single stroke, Weinberg or Salam solved three fundamental problems. The masses of the gauge bosons, they become massive. The masses of the charged leptons, which also is important because in a chiral theory, you cannot put by hand masses of the leptons, and also the glacial-electroweak mixing. So the same mechanism, the Brout-Engler-Higgs mechanism, if you want, is responsible for all that. The masses of gauge masses of practically everybody, and also the glacial-electroweak mix. Now, yet this paper, and also it's very beautifully written. If you read a Weinberg paper, it's in his classic style. It's really fun, very simple, very explicit, very well written. And still, it went completely unnoticed when it was first published. I remember again at CERN, we had with all the young fellows who were there, we had a study group trying to study papers of the literature. In our group, the Weinberg paper was presented by the late Bruno Runner, and we all decided unanimously that it was totally uninteresting. We forgot promptly everything about it. Why? Well, first, I think it was the title is uninspired because it's called Model of Leptons, a model of leptons. Now, the only leptonic, there were good reasons for that. At that time, he could not write the extension to hadrons. But if you read the paper with the title A Model of Leptons, the only leptonic weak interaction process was known at the time was muon decay. So having a model, specific model with complicated things like gates theories, non-abelian gates theories, spontaneous symmetry break-ins, mixes, blah, blah, all that, just for one decay, for one process. It was like taking heavy artillery to kill a fly. Furthermore, all the problems the three fundamental problems that this paper is solving were not considered as not even as problems, let alone fundamental, by the theorists of that time. Since we don't know whether the gauge bosons exist, why should we care about how they get their masses, etc., etc.? It has practically no citations before 72. You can check that in the archive. When we published the paper on charm in 1970 with Glasso and Maiani, none of us, three of us, had any recollection of it, and we do not cite it. Even worse, even Weinberg had forgotten it. I will come back to this point in a moment. After 72, of course, the number of citations skyrocketed. It was obvious. So, I will try to describe the history of how the ideas, what happened, and then this paper, which is one of the most fundamental papers in our field, was resuscitated. People really understood it. So it went through many steps. The first thing is the study of the Fermi theory as an effective field theory. Now, the Fermi theory of weak interactions was a most seminal and inspiring model. Study its symmetry properties had given rise to current algebras, to many important things like chiral symmetry and all that. But it's not normalizable. What it means? It means that it requires a cutoff. In other words, if I have some quantity A and I want to compute it in a power series in the Kaplan constant GF, then I can write this series the following way. A1 GF, the first coefficient, and then a series in which I start from 2 to infinity, and then I have GF lambda squared to the power n minus 1 in this particular case. Right? So I put all the terms with the highest powers of lambda squared, leading divergent terms. Right? You see that, in fact, GF lambda squared, which is a dimensionless quantity, acts like as an effective Kaplan constant. This is what I call an effective field theory. Now, the expansion obviously will become meaningless when this effective Kaplan constant is of order 1. And if you take the value, the numerical value of GF, you find that lambda is around 300 GeV. Now, for the physicists of the middle 60s, 300 GeV was essentially infinite. The accelerator at CERN, the most powerful accelerator, was 30 GeV. So 300 was nothing. Then came, in 67, came a paper. There was a series of papers, but the first ones and the ones that I find as most explicit was Yoff and Shabalin from the Soviet Union. And they noticed something which is worth thinking about. It is the vital importance of precision measurements. You see, let me rewrite the story, the series I had before, but now I keep also next to leading terms, next to leading terms, etc. That means I don't take only the, you see, this, only the lambda square to the n power, but also I look at lambda square to the n minus 2. So higher powers of GF with less powers of lambda, right? So I can again write all this expansion, the leading divergences, which have only the effective thing, and then the next two leading terms that have an extra GF here, and then for dimensional purposes, you have an m squared, which will be of order of 1 GV or something, and then next to leading, etc. So let me look at the leading divergences. Leading divergences mean, let's say, in an intermediate vector boson theory, although their argument was in current algebra language, not in field theory language. But we can think of it like that. So the leading divergences are the emission of a virtual W and reabsorption, right? So they contribute to processes that we would call strong interaction processes. But since the vertices are weak interactions, they violate things like parity or strangeness. So it means that G effective cannot be of order 1, because otherwise you would have parity or strangeness violations of order 1 in strong interactions. And for example, Joff and Sabalin looked, for example, in nuclear physics, in the energy levels nuclear physics. You don't see say, mixing of and different parity in of order 1. So they looked at the precision measurements, which was the absence of parity and strangeness violations in strong interactions, and they found that at that time the agreement was taxons of the order of 10 to the minus 4, so which means that they gain a factor of 100 in the cutoff, so the cutoff was lambda 3 GeV. Why did most people not worry about it? Now, this was a terrible result because 3 GeV was explorable at that time. We were making, experimentalists were making experiments at 3 GeV, and they had not seen any effects of higher order weak interactions. How come? Why most people did not worry about that? I suspect that the main reason was a widespread mistrust towards field theory in general and higher order diagrams in particular. I remember very well when I tried to discuss with some people in the certain theory division, they were telling me, oh, come on, that's nonsense. Since we have no theory, why bother about these higher order effects? Once we had the right theory, all these things will be solved. Studying the higher order effects of weak interactions was useless in the absence of a full theory of strong interactions. They would say, yeah, but these things, we don't understand strong interactions, so why bother about weak ones? However, Joff and Sabalin had pointed out that if the strong interaction, if the strong interactions respected current algebras, say SU2 cross SU2 or SU3 cross SU3 or whatever, then they could not provide a cutoff for these effects. So it was hopeless to try to hide the problems behind the strong interactions. But few people had understood this. So then started what I call fighting the infinities. A very long list of attempts to change something to make the theory more convergent or better behaved or something. I will mention some. very quickly. A complete list should include many more. So, for example, T.D. Lee and Giancarlo Wick published a paper which was interesting because they said, suppose that the physical Hilbert space contains states with negative norm, negative metric. And for example, let's assume that the vector bosons of the Wick interactions are such states. Now, usually you say, oh, that's nonsense, because if you have states with negative norm, you violate the conservation of probabilities. But then Lee and Wick said that, well, if these particles are very massive, they have a very short lifetime. So these violations will be confined to very, very short times and probably be non-observable. Another, Kumar and Segre in 1965 had another idea. They said, well, why is Fermi theory non-normalizable? Because it has massive vector bosons. Well, let us assume it has scalar bosons. And then by clever fit transformations, some processes would look like vector processes by fit transforming. Well, it went unnoticed because by that time, people were 65, people were already attached to chiral symmetry and the fundamental significance of the vector currents in Fermi theory. So this paper went practically unnoticed. Then there was a paper by Gell-Mann, Goldberger, Kroll, and Rowe in 1969 again, in which they said, well, let us take a theory which does not have just one vector boson, but a collection of vector and scalar bosons. And then, if you are clever enough, you can arrange the couplings so that all these dangerous divergences disappear, at least to matrix elements where you can measure them. The other, where you don't measure them, it does not matter. So it is a very intelligent paper in some sense, but very complicated. Glashow has this sentence for that paper: few would concede so much sacrifice of elegance to expediency. Then from Italy came a series of papers by Cabibbo and Maiani, Gatto, Sartori, and Tonin, which had the idea was to cancel the divergences, but for a particular value of the Cabibbo angle. And although the program did not succeed finally, they had some interesting relations among the Cabibbo angle in terms of the quark masses, and also another thing which turned out at that time it was considered as stupid, because you see they claim that the mass difference between the down and the up quark is of the order of the masses themselves. So isospin is very badly broken in the quark level. At that time, now we know that it's correct, but at that time it was considered as weird. And then by the late 60s, a long and painful struggle against the infinity started. Although it was fought by few people, it has been an epic battle given in two fronts. The first is what I call the bottom-up approach, or the phenomenology front. It aimed at finding the necessary conditions to the theory in order to push the cutoff beyond the reach. So it was not to find the fundamental theory, but find the conditions under which a theory could apply. And complementary to that was the top-down approach, or the field theory front. Find the conditions under which a quantum field theory involving massive charged vector bosons is renormalizable. This one was fought mostly by Tini Veltman and after 1969, Gerhard Hooft. Right? It took the success of both fronts to solve the problem. So let me start with the bottom-up approach, which is the one, of course, I know more because that's the one in which I was involved. So we start with the leading divergences. They raise the spectrum of strangeness and parity violation in strong interactions. Now, this was a paper in '69 by Bouchard, myself, and Jacques Prentke. So what was the argument? At the limit of exactness U3 crosses U3, you cannot define things like strangeness, right? Because you can make rotations, you can choose any basis in the quark space, and then strangeness is not, you can perform independent right and left-handed rotations in flavor space. As a result, any net effect should depend on the part of the interaction which breaks as U3 crosses U3. So in a completely symmetric theory, these effects do not exist because there is no such thing as a strangeness violation, and the same thing you can do for parity in these things, right? So what we proved is that if the chiral symmetry break, now you know that as U3 crosses U3 must be broken. If you choose the Lagrangian, the break in Lagrangian, which now depends, which belongs to a 3-3 bar plus 3 bar 3 representation, then all the leading divergent terms are diagonal in flavor space, both parity and strangeness. So they don't have any of these dangerous effects. Now, this breaking is just the quark masses. So putting explicitly quark mass terms breaks chiral symmetry, SQ3 crosses SQ3. And if this is all the breaking there is, then everything works okay. Now, this particular form of the breaking corresponds to what everybody liked, was the favorite one to most theories. So this was considered a welcome result. So everybody liked the result, and I generalized in our first paper, it was one loop, and then I generalized it the same year to all orders. So this was sort of the easy part because it solved the problem without changing making any important changes to the theory. The theory was more or less what everybody liked. And then came the next two leading divergences. They induce k long to mu plus mu minus, or a large decays, or large k0, k0 bar mass difference. It is the paper of Glashow, myself, and Luciano Maiani of 1970. So as I said, the solution of the leading divergence problem was found in the framework of the commonly accepted theory at that time. On the contrary, the next two leading divergences required a drastic modification, although in retrospect, it's a quite natural one. It's almost obvious. In fact, as you understand, I have been teaching this subject for many decades to students, and it was so trivial that it was hard to convince the students that this was not, it was anything else than just a trivial exercise. You see, the early Fermi theory had a kind of lepton-hadron symmetry. You have two leptons, E minus and neutrino, and two hadrons, neutron and proton. The discovery of the first heavy flavors seemed to break this symmetry. We had four leptons, electron, neutrino, mu, and this neutrino, but only three quarks, neutron, proton, and strange quark. So the Cabibbo current had a piece which, well, you had only one quark with 2/3 charge, so it's U, the up. So, but you have two quarks with minus 1/3 charges, so you had a combination. And the orthogonal combination, the, say, minus sine theta d plus cosine theta s, was not coupled. It did not participate in the weak interactions. Notice the difference with the leptonic current. The leptonic current has nu bar E plus a mu bar nu mu. So there are two separate pieces, right? Because you have four leptons. Now, if you look at the leptonic current and you try to take the commutator of the two charged currents to find the properties of the neutral current, you find no lepton flavor change in pieces, because precisely there are these four things. So the problem was the first level of the problem, if you want, which is the commutator of the zero components of the Cabibbo currents. It contains this d bar C DC, which has flavor change in pieces. It is the reason why Weinberg's model applied only to leptons. Right? That's why Weinberg could not apply his model to the quarks. The leptonic part, as I said, had no lepton number violating problem, so the solution is obvious. Restore lepton-hadron symmetry. Introduce a fourth quark. So if you have two pieces, now with the C, you have the other piece, the orthogonal combination of the D and S quarks, then the commutator J and J dagger is diagonal in flavor space. So it has no problem. It turned out that there was also a second level of the problem, which was more subtle. The three-level solution is not enough to explain the observed phenomena. For example, decay along to mu plus mu minus decay could be generated by this diagram, this square diagram, right? D bar S, K0, goes to mu plus mu minus. Now you say that's second order weak. Yes, but if Joff and Sabalin are right, they produce effects that are too strong for the observed rates. Now, if you have, however, the second quark, the fourth quark, so you have a second diagram in which instead of U, you have C. And it's easy to verify that the sum of the two diagrams, if the mass of the U were equal to the mass of the C, they would cancel exactly, because you have the difference of sine and cosine with minus sign. And so because of the mass differences, the sum of the two diagrams will be square mass of the charm U over MW, which is good. Well, mu is very small compared to MC, so this gives something like GF times MC square, which gives you a limit on the masses of the charmed quarks, which were of the order of the Joffen-Sabalin thing, that means 3 GeV. So the argument showed that not only you predict the existence of a fourth quark, but you also say that it cannot be too heavy, arbitrarily heavy, right? And this is important because if a thing is arbitrarily heavy, then a prediction of something arbitrarily heavy is not very useful. So some personal recollections of this thing. Enthusiasm. Glashow. We expect our work to be part of future physics textbooks. In fact, he was right when he said that. It was right the moment, the day we discovered this mechanism. And we, Luciano and myself, were thinking that he exaggerates. Well, he was right. We jumped immediately to my car and drove to MIT. We organized a seminar in Franz Low's office, and with practically all the MIT theorists. I remember Low, of course, but also Steve Weinberg, Sergio Fubini, Gabriele Veneziano, Roman Zakiv, was there? Johnson, well, maybe others also, I forget. So we presented all our work very carefully, and there were lots of questions. Took 2 or 3 hours on the blackboard. Francis Lowe praised our solution. There were no objections we could not answer, and we felt very confident. In fact, in this seminar, we said that now we can have the theory can be a Young-Mills theory. But how can we give masses to the vector bosons? None of us had any recollection of the Brauthen-Higgs or Weinberg paper. Steve Weinberg was there. He asked many questions. He liked the approach. He did not make the connection with his previous work. Even he had forgotten his previous work. We were happy with the seminar at MIT, but we met skepticism everywhere else. Mostly myself, because I had to teach, but also I had also to find a job I was a postdoc at Harvard, so I had to find a job. So I traveled all over the place in the United States to give seminars on that. And it was really an disappointing experience. The objections were all sorts of strange ones. Some were claiming that a fourth quark in this mass range is excluded experimentally. Since I did not know all the data, I had to spend lots of time reading all the, and I found no such claim. There was no reason, but people were convinced it was true. Others were questioning the very idea of ordering the divergences, leading divergences next to leading, say, logarithmic versus power and things like that. So they claimed that's meaningless. And even they were saying derogative statements. Oh, you mean that lambda fourth is worse than lambda square? Why? And things like that. The main objections that were not just taste of them, but not of taste, were a profound belief that weak interactions could not possibly give us information about the structure of the spectrum of the kind of physics that quarks live, that this should be decided by strong interaction arguments and basically were bootstrap arguments. So everybody was saying that trying to guess the form of the elementary constituents of hadrons by looking at their weak interactions is hopeless and it's stupid. So this was the skepticism I had to fit in this everywhere else. Now let me change and talk a little bit about the top-down approach, which was mainly the work, as I said, of Altman. I say in historic times because I'm not sure if there were other people before who tried to look at Young-Mills quantum field theory as the dynamical theory of weak interactions, as a quantum field theory looking at higher orders and things like that. As far as I know, the first was Tiny Weltman. Now, his method was a direct attack. Compute until you hit a problem, and then come back and look what happened. So he started by looking at charged, massive, charged vector bosons, because he said no matter how, whether there are, don't forget that at that time we did not know whether neutral currents existed or not. So he could not start with any of this. He said no matter what the theory is, there will be charged vector bosons, massive vector bosons. And there is also a photon. So let me look at those three. And he found that the theory is not normalizable, had all sorts of divergences, but he found a particular thing that many of these divergences canceled for a particular value of the couplings of the charged vector bosons to the photon. Normally, you have the charge, you have magnetic moment, and quadrupole moment. And if you have a particular value of these three, then many divergences cancel, which means, now it turns out that this is particularly the value that you would have if the three were forming a triplet with a Young-Mills interaction. So this was for Weltman was really the signal that the Yang-Mills theories, he was on the right track. The complexity of the calculations forced him to write the first program of symbolic manipulations, which he called Kunship, which applied theoretical high-energy physics. He often had to reinvent everything, including the Feynman rules. As you know, Feynman had guessed you see, the rules are not the naive rules that you would obtain, say, by generalizing QED. For a covariant gauge, you have to introduce what we call today Fadejev and Popov ghosts. Feynman had guessed this, the importance of these ghosts, but not because he studied Yang-Mills theories. He was not interested in Yang-Mills theories. He was interested in gravitation. So he looked at there is a set of lectures which has been published in Acta Physica Polonica, and it's quantum gravity. Now, he looked and realized that if you look at a loop, closed loop, let me say it differently. In covariant gauge, the propagator propagates physical but also unphysical degrees of freedom. And he noticed that in a closed loop, the unphysical degrees of freedom can go around the loop and never get killed by anything. Now, Feynman being Feynman, he understood better than anybody else that a quantum field theory, at least in perturbation expansion, is defined by the Feynman rules. So he said, well, I change the rules, and for every closed loop, I introduce fictitious fields which turn the other way around and cancel the unwanted transition. And he checked, that is the interesting thing, he wanted to check that this was right, and because calculations with gravity were complicated, he looked at the Yang-Mills as a laboratory for gravitation. And he checked that was right. And as you know, Fadejev and Popov found formal proof of the statement, which applies to all orders, using the Feynman path integral, for that matter. And since that time, we call these ghosts Fadejev-Popov ghosts. Also, by trial and error, Weltman discovered the need for the addition of a physical scalar field. He had no idea of what had happened with Brautengler, Higgs, and all that. And by looking at the divergence of the theory, he said that really, to cancel all divergences, you need also an extra scalar. It's what I call extreme compartmentalization in high-energy physics. Everybody was studying only his own field, and nobody was looking at anything else. In 1969, Weltman was joined by a graduate student named Gerald Hoft. Gerald attended the Cargès summer school. In fact, it's funny because he first applied to go to the Lejeune school, but his application was turned down. So he went to Cargès instead. And he followed Ben Lee's lectures on the spontaneous breaking of the sigma model. So for him, and he told me that several times, that was a revelation. He understood the problem of spontaneous symmetry breaking and phase transitions in field theory and all that. So when he went back, joined with Weltman, and the work they did together has revolutionized the entire field of theoretical high-energy physics. It showed the mathematical consistency of the electroweak theory and made possible the discovery of asymptotic freedom and QCD. I go one step further, and in the fall of 71, I follow more or less my recollections. In the fall of 71, I joined the theory group at Orsay and started again my collaboration with Busquin and Meyer. We tried to understand at that time, Hoft had published his first paper on the normalizability of massless Yang-Mills, and then followed afterward with the papers on the massive ones. We tried to understand the properties of the normalizability properties, which were very, very complicated because the proof of Hoft and Weltman were diagrammatic. So you had to go through the diagrams and see cutting rules. You cut the diagram to put all the intermediate particles on the mass shell, etc. So it was a complicated proof. So, but then we understood that for the proof to work, you needed absolutely the word identities. The word identities had to be exact. But for the SU2 cross U1 theory, the axial current has anomalies. The word identities are violated, and then we proved that the normalizability does not fails. The program does not apply. You can verify this explicitly in this simple model. We take U1 cross U1. You don't need the entire SU2 cross U1. And then you have the B, the vector boson and the scalar, the Goldstone would-be Goldstone boson. And you see that because of the word identity, the pole, the k² equals 0 pole cancels in these two diagrams, but it does not cancel, of course, in those diagrams because of the anomaly. So the anomaly brought by the triangle diagram invalidates the word identity. Solution. So this was found independently by Bousquin, Meyer, and myself, but also Gross and Zakiv. The important observation is that the anomaly is independent of the Fermi mass. You see, in the loop here, the triangle loop here, you don't, all masses, every fermion which coupled to those currents will go around. You don't, whether it's heavy or light does not. For the electroweak theory, this means that we need both the leptons and the quarks. You cannot look at the anomaly only on the lepton. So that means if you want the Weinberg model by itself was not normalized. You need the quarks also to make it normalized. Each one will go around the triangle. A simple calculation shows that the total anomaly produced by the fermions of its family will be proportional to the sum of the electric charges, which for the standard model vanishes. The moral of the story is that families must be complete. You need the C quark, because otherwise the second family is not complete. And once you discover the tau lepton, this implies the existence of the B and top quark. Families must be complete. Furthermore, there is another thing which is interesting. This anomaly cancellation should occur at every level of compositeness. For example, you could imagine writing the standard model before the invention of the quarks. You didn't need really that. So you would have proton, neutron, and electron and neutrino. Well, the anomaly cancellation is correct. It works. And then you go to the quark level again. If tomorrow you find out that quarks or leptons or whatever are composed by other things, in this level of compositeness also the anomaly should cancel. They should cancel at every level of compositeness. So the scheme which became the standard model was fully written in 1973. It is a quantum field theory which is normalizable and invariant under gauge transformations, spontaneously broken U1 crosses U2 crosses U3 to U1 electromagnetic times SU3. But it was not fully accepted. For most physicists, it was a wild theoretical speculation with no connection to the real world. It contained too many assumptions for too few experimentally verified predictions. In fact, all ingredients of the standard model seem to contradict experimental facts. As a result, unknown and complicated mechanisms had to be invented to hide the difficulties. I'm sorry, I see that I'm running out of time, so I will go faster. So, the price of the standard model. I put myself in the London conference in 1974, the Rochester conferences, this series of these conferences that at that time were called Rochester Conference, was in London and was organized by Abdul Salam. He asked me to give a report on gauge theories. In fact, if you look at these conferences, they represent more or less the state of the art in our field. And in all previous conferences, there was a plenary session on weak interactions and another plenary session on strong interactions. In London conference, Salam had decided to have one plenary session on theoretical high-energy physics, gauge theories, and asked me to give the talk. And I believe this was somehow the change of attitude and of how we looked at our field. Now, what were Young asked me after the talk how I could convince experimentalists to look at gauge theories. And of course, I gave some answer to that. But in fact, his question was a very profound question. Because let us see what were the predictions of the standard model. Gauge symmetry. Gauge symmetry means gauge bosons. How many? 12 of those. But we only knew one, the photon. What happened to the others? Then either they were very heavy with some obscure mechanism, Brautengler-Higgs mechanism that nobody understood, or unobservable because of confinement. So totally strange ideas just to hide the fact that we did not see 11 out of the 12 predicted gauge bosons. BH mechanism, one or more scalar bosons, rejected by many people because people were saying, come on, you were telling us that all weak interactions are vector interactions. Now you tell us that there is also a scalar particle. Unknown mass, furthermore, that nobody knows how to see. Neutral currents. There was already a first, say, observation, but I will come back to that. A fourth quark. This was really the prediction that most people found hard to believe. To summarize, we theorists, trying to tell everybody that some obscure higher order effects, trial diagrams for anomalies, or square diagrams for flavor changing neutral currents would dictate the structure of the world. Admittedly, it takes a solid faith in quantum field theory to accept such a claim, and most people did not have that faith. Gargamel had already observed the neutral currents. Candy gave a report in the London conference in which he said, those of you who have bet on neutral currents, now is the time to pay and collect. I have won some great wines betting 4 neutral currents against my skeptical colleagues, incidentally. Many people were not convinced. I go very fast. There was only a single electron event. Most people don't believe one event. It was a large international collaboration, 55 physicists. I don't know what they would say today. Well, there was a problem with control of the neutral background. The chamber was 4.8 meters long, but only 2 meters in diameter. So you could not exclude neutrons coming from the sides and mimicking a neutral current. For that, Hyde had to write a very complicated, and it was, I believe, the first, sophisticated Monte Carlo algorithm which simulated a large and complex detector. And many people did not believe in these things. The final thing that people did not believe was the rise in R and the hidden charm. The ratio R, defined as E plus E minus 2 hadrons, E plus E minus 2 mu plus mu minus, by QCD was predicted to approach a constant value, which for that time was 2, and from above. And these were the results. These were presented by Barton Richter in the same conference. Now, 2 is here. If you can see these points approaching 2 from above, most people said that, you see, this is for most people, this was a proof that all these things were just nonsense. Well, I skip that because this was the proof that goes 2 from above. So, in my report on gauge theories in the London conference, I said, The hadron production cross-section, which absolutely refuses to fall, creates a serious problem. The best explanation may be that we are observing the opening of the charm thresholds, in which case everything fits together very nicely. You see, if you are charm would add 4/3 to R. And furthermore, accidentally, tau, which was happened to be at the same time, at the same place, same energy region, you see, that too, with charm it goes up here, but now tau really, no, up here, now tau brings it up here, and then it starts making sense, right? Well, in November 74, Speer decided to go back and sweep the region above 3GV in fine steps, and to their great surprise, they obtained a totally different picture. Here it is, this is the J-psi discovery, which settled the issue. In December 74, one day, Andrea Garrigue called me and asked me to come in an improvised meeting because there would be some fantastic announcements. Gerhard Hopf was visiting the Color Mouth, so I took him with him along. In this meeting, Bernard Jean-Marie had just come. You see, at that time, news did not travel with the speed of internet. Bernard Jean-Marie had to take a plane from Stanford and from San Francisco and fly all the way to Paris to give us the results. And the results were this 3.1 GeV mesons decaying to pions via strong interactions with less of 100 keV. When Lagarde asked me what I thought, I said, no, that's impossible. And it's Gerhard Hopf who first pointed out to me that QCD could explain that. And as we know, he was right. I will go fast, because now I'm out of time. And
Professor Iliopoulos, yes. we have a break for 30 minutes, so there is some more time if you need it.
Pardon, excuse me.
I said so we have 1.5 hour talks, and then we have a 30-minute break. So there's more time if you need to explain things.
Okay, fine. Okay. Yeah, well, I will stop earlier, don't worry. So, as I said, it was Hopf who first gave me the right answer. And today, you know what is. There was at that time a rule called the Kubo-Zweig-Iizuka rule, which is another empirical rule with no theoretical foundation in the Dark Ages. The rule said that if you have a state with a boson with a quark and diquark, the decays which require the annihilation of this pair and then creation of new ones are highly suppressed. And this you can verify it's true for the phi measure, right? Now we understand with QCD how it goes, right? And because you need 3 gluons and all that. And in fact, if you look between, say, 1 GeV, which is the phi mass, and 3 GeV, which is the J psi mass, the alpha strong, the strong interaction Capri constant has dropped by a factor of 2. So to the third power, it's 8. So if you look at, if you take the width of the phi to kk bar, to pionic width, which is 650 kV, and divide by 8, you find 80 kV. Very nice agreement. The chronology of the discoveries as they appeared in the physical review letters. The first paper, the Brookhaven paper by Aubert et al., was received November 12, 1974. Then a day later, November 13, was Augustin et al. From Speer, right? Which they have, of course, a much more. They are the ones that have the very narrow widths because they have very good resolution in the width, and a little bit later, November 18, Adone made the same, from Roma, Frascati, they observed the same J psi resonance. So it's also. Now, there is a paper, a theoretical paper with reception date November 19, which has all this argument by Appelquist and Politzer, and I believe, although I never checked that with them, that they must have thought of it before the discovery. I don't believe that between November 12 and November 19, also because they did not know the results of that well, they invented all that. So I believe that this was a prediction, but I have to check with them, I'm not sure. The long road to verification, the real charm and heavy flavors. Here they are. You see, this is the R. You see, you have J psi, you have psi prime, and then you have the wide resonance. Of course, if you look under this wide, it means since they are wide, means that they have gone above the threshold for charm and H-charm production. So you can find charm particles under them, and really they found them this way. Families are complete. Existence of tau implies B and tau, as we said. So the real charm and heavier flavors. Mesons with naked charm were naturally discovered among the decay products of the broad resonances we see above for GV. This happened in 1976. In the meantime, a rich harmonium spectroscopy was discovered in full agreement with theoretical predictions. Although nobody paid the bet I offered in the 74 conference, the entire 76 one was indeed dominated by charm particles and gauge theories. The phase transition was complete. I had made an offer of a bet. I have won already several bottles of wine by betting for the neutral currents, and I'm ready to bet now a whole case that the weak interaction sessions of this conference, if the weak interaction sessions of this conference were dominated by the discovery of the neutral currents, the entire next conference will be dominated by the discovery of the charm particles. In fact, it was true, and the phase transition was complete. By 76, nobody would doubt or that the standard model was the right theory. So, what next? Well, let me look again at the ratio R. It's very intriguing. This is now all the way up to the Z mass, right? And then you have both the J psi's and the B resonances, the Y particles. Now, what is the lesson? You see, as we said, the Parton model, as completed by QCD, predicts R more or less a constant, say slowly approaching a constant from above. Okay, and except, of course, when there are strong interactions, like in low energies, you have all these resonances, and then pretty soon the R settles down to, you see the green curve is the Parton model, and the red ones include the QCD corrections. So you see that it follows quite well, these are points, the Parton model prediction. Then you approach this thing, and of course everything breaks down because you have resonance. But again, after that, you have settles to, and then settles to a new, after you go above the charm threshold, it settles to a new plateau here. Again, you have the B quark and settles to a higher plateau, but B has small mass, so it's not very big. Okay, so, and it works. It's a remarkable agreement. Somehow, and don't forget that this prediction is just lowest order perturbation theory. It's nothing else. And it's applied to QCD, which is, it's not QED, it's not the coupling constant, it's not 1 over 137, it's 1/5 or 1/10 or something like that. So why does perturbation theory work so well? It's a striking feature of the data, that perturbation theory outside, of course, the region of strong interaction, works very well beyond any expectations. Why? We don't know. I mean, if you make any order of magnitude estimation, you would have found that for QCD, it should have broke down much before. It seems that let us take that as an experimental fact, saying that perturbation theory can be trusted even if we do not fully understand why. Now, in a talk I gave at a meeting of the European Physical Society in 2011, I said, I want to exploit this experimental fact and argue that the available precision tests of the Standard Model allow us to claim with confidence that new physics is present at the TeV scale and that LHC can probably discover it. The argument assumes the validity of perturbation theory, and it will fail if the latter fails. But as we just saw, perturbation theory breaks down only when strong interactions become important, and new strong interactions imply new physics. My conclusion was that for LHC, which was about to start, commissioning soon, new physics was around the corner. Today, we know that LHC found no corner. But I secretly believe the argument is correct. Only the corner is a bit further down. Although I will not see it, I'm confident some of you will find it. Thank you.
Thank you very much. We wanted to open the floor for any questions. So yeah, first of all, I guess I'll go first. I was wondering if you could talk about, you mentioned when you were first entering graduate school, there were no quantum field theory courses and that people were against quantum field theory. And I was wondering if you could say something about, there's a lot of work on S matrix theory, ray J trajectories and so on and so forth. And I was wondering about your opinion. And there's a book by Geoffrey Chu, it's called The Analytic S Matrix. And he has all these speculations relating to nuclear democracy. And so I was kind of wondering about your sort of thoughts on nuclear democracy at the time. Did you think that quantum field theory was wrong? Or, did you believe in quantum field theory? What was your opinion of like S matrix theory versus quantum field theory?
Yes. I can tell you what I remember. First of all, let me say that this approach, the analyticity, say, approach, say, Berkeley School, whatever you can call it, was raised to maybe exaggerated heights of faith. It was almost a religion, but then it fell to equally unjustified depths of oblivion. In fact, this school has produced very many interesting physics results, which have become part of our culture, like Reggie behavior, or Lorentziano amplitude was in that school, string theory, bootstrap techniques. All these things have survived and are part of our culture today. It's just that at that time they were sort of religious faith, that everything else was. Now you said about teaching. Yes, we had courses on analytic S matrix theory. We did not have courses on quantum field theory. In fact, the first course I had on quantum field theory was by Maurice Levy, which was on a non-local version of quantum field theory. So before learning local quantum field theory, I learned non-local quantum field theory because he had this theory non-local QED. But it was not part of the curriculum in most universities, not everywhere. I checked in some places they had courses of quantum field theory. But when I went to CERN as a postdoc, my fellow postdocs, which were coming from all over the place in Europe, most of them had no courses on quantum field theory like me. So because it was meant to be only for QED, Peterman had computed the two-loop, say, G minus 2 to the electron, but was not considered as a great thing. Who cared? I don't know if he answered your question. Yes, it was a complicated thing, and I think that the two extremes are bad. We should not consider that everything that happened there was useless, but on the other hand, we should not consider that was the religious thing. So it was good. In fact, I do believe that theoretical physics is like a Monte Carlo algorithm. So at every time, randomly, we look at various directions. We pursue the ones that look more promising. Occasionally, we find out that they lead to a dead end, so we have to come back and start a new direction. But this is how physics works. And of course, we don't teach physics this way because it would have taken too long time to do it. And we give the impression of having a well-defined goal, somehow a unique line of thought, which is not true.
Yeah, thank you. That answers my question. Are there any other questions? Well, I also wanted to ask about the standard model itself. When did you, I think I read that you were the first person to present the standard model in full form. And I was kind of wondering sort of the chronology of the standard model in terms of theoretically, writing it down. Were you the first person to propose that there was a standard model? Was it Weinberg?
No,
What's sort of
no,
the
no,
chrono?
no.
Okay. Mhm.
I was not the first person to propose the standard model. The standard model was built, as I said, Weinberg and, well, I tried to explain Glashow, Weinberg and Salam, then the various additions to make it work. Veltman and Hoff to prove that it's normalizable. But this part was the electroweak model. Then something I did not talk because I did not work on it was the say asymptotic freedom and QCD, which is another very beautiful story. And it was this was by 73. So in 73, people had put all that together. So there was the standard model was ready. It was written down perfectly. And if you look at the parallel sessions in the London conference, there were sessions on QCD, there were sessions on neutral currents. So parallel sessions, they were studying various aspects of this model. But there was no, it was not generally accepted because, as I said, most people thought that we were sacrificing, we were just making wild speculations. And every time we had a problem, we said, oh, put a fourth quark or put something. Most people were not ready to accept this kind of arguments. Quarks were what we find in hadron structure, and there was no question about that. So it was the first time I defended it, I think. I was the first to defend it, but I was not the one who made it.
I see. Thank you. Are there any other questions? It's fine if there's no
Okay.
question. Yeah, Professor Iliopoulos, yeah, thank you very much for your time. It was an honor to hear from you.